Hello, I'm Martin Looker. Ambient IoT is one of the fastest growing sectors for the Internet of Things, with numerous device makers looking to create high performance and reliability devices whilst running without batteries. In this video, I'll show you how to get started creating Bluetooth applications using the new energy harvesting kit developed by Silicon Labs and EPs. And there'll be links to all the resources shown in this video in the video description. Before I get into the details, we'll take a quick look at a couple of example applications. The first uses a photovoltaic cell to charge a capacitor that the SoC is running from. It regularly measures a power supply voltage and includes it in a Bluetooth advertising packet that can be read by a second device acting as a Bluetooth observer. The debug messages that you can see on screen with the voltage measurements are output by the observer device, and data from the received packet is displayed on its OLED screen. This setup is ideal for sensor type devices where you can't run power and don't want to use batteries for environmental reasons, or because the device may be installed in a hard to reach location. The second uses a kinetic switch. When the switch is pressed, enough power is generated to transmit Bluetooth advertising packets. Once again, our Bluetooth observer device outputs debug messages when the Bluetooth packets are received. It also toggles the observer's LED on or off and inverts the OLED display to indicate a light state. This setup works well where you want to control devices, again without running power or using batteries, whilst allowing the freedom to mount the device easily or even allow it to be portable. The wireless connectivity is provided by the Silicon Labs EFR32xG22E SoC. This E series of chips has been designed to offer low power operation, with a focus on energy harvesting applications, and includes a faster boot sequence compared to other similar chips. For this video, I'm using the Silicon Labs EFR32xG22E Explorer Kit. The SoC in this kit supports both Bluetooth and IEEE 802.15.4 protocols such as Zigbee. The board features a user button and LED, but is expandable thanks to the quick connector to which a wide range of sensor boards can be daisy-chained via its I2C bus. It also features a micro E bus socket for further expandability. And for energy harvesting applications, this socket is used with the boards from the energy harvesting kit. These also allow additional micro E clipboards to be stacked on top. The energy harvesting kit provides 3 boards focused on energy harvesting, plus an XG22E Explorer Kit. So let's look at the 3 energy harvesting boards. The first is the battery backpack. This obviously isn't intended for energy harvesting use, but allows users to take measurements from multiple points in the power supply circuitry in order to compare power usage between battery and battery-free designs. Note that all the boards in this kit have these test points to allow easy monitoring of power usage. Basically, this board is provided to allow a baseline for application power requirements to be established before introducing energy harvesting technologies. The second board is the dual harvester board. The main component is the EP's AEM12920, which is their most advanced PMIC. It can be configured via the I2C connection to the SoC on the Explorer Kit board. This is the most flexible board, allowing a wide range of energy harvesting and storage devices to be connected. We saw this in use with a PV cell and capacitor in the short demo earlier. It can cater for both DC and AC sources, including simultaneously, and a regulator and rectifier are included for use where required. This board is all about collecting and storing energy and using it over time. The third board is the kinetic switch. that allows the development of batteryless devices based on switches and buttons, where power is only needed when the button is pressed and released. There is no storage element used in this case. The button itself provides enough energy to briefly power on the board and perform some communications. An EP's AEM00300 PMIC handles the power and is configured to provide the optimal power from the kinetic switch. The focus of this board is to make use of bursts of energy when an action such as a wireless transmission needs to take place. We have also designed a 3D printed case for the Kinetic Switch and Explorer Kit boards. With the boards fastened into the case, pressing the button activates the application. The design files for printing the case can be found in our Open 3D Print Prototypes repository on GitHub. Software support is provided by the Energy Harvesting extension for Silicon Labs Simplicity Studio version 5 IDE. The files for the extension can be cloned or downloaded from the GitHub repository and then installed into our Simplicity SDK with just a few clicks. Doing this provides access to the EP's AEM13920 PMIC driver software component, and you'll need to allow evaluation components in the quality dropdown to access this. Once you've installed a component into your project, you'll be able to make use of the APIs to configure the PMIC, and these are described in the driver README in the repository. For quick evaluation and to start exploring example code, go to Simplicity Studio's launcher perspective, select a connected EFR32xG22E board and search for harvesting. The demo options will flash pre-built binaries into a connected board when the Run button is clicked for quick evaluation. To explore the code, look for the example projects. Clicking the Create button will add a new project to Simplicity Studio with code that you can explore and adapt. The available Bluetooth demos and examples are Bluetooth SoC Energy Harvesting Sensor. This is the example we saw running earlier with the PV cell and capacitor on the dual harvester shield, and is built on the standard Silicon Labs Bluetooth stack. The Bluetooth Rail SoC Energy Harvesting Sensor implements the same application but makes use of the low-level Rail radio APIs in such a way as to make the application more efficient than using our full Bluetooth stack, which is built on top of Rail. Bluetooth Rail SoC Energy Harvesting Kinetic Switch. This is the example we also saw running earlier, using the Kinetic switchboard. This example again uses the low-level Rail radio APIs for maximum energy efficiency. The use of our full BLE stack allows experimentation if you have existing projects you are looking to power through energy harvesting. But using Rail to control BLE is the most energy efficient way to construct such an application. So you may choose to begin with it for new projects or move to it for existing projects. Bluetooth SoC Energy Harvesting Application Observer. This final Bluetooth example is the observer device we saw earlier. This doesn't use energy harvesting as a power source, but instead receives the messages transmitted by the energy harvesting devices, outputs them to the debug serial port, and, in the case of received switch messages, toggles its LED. I've added code to the observer to also output some of the observer's data to the OLED by making use of the third-party hardware drivers extension for Simplicity Studio available from GitHub. This extension has drivers and example applications for a wide variety of add-on boards, many of which can be connected using the Quick or Micro E connectors on the Explorer Kit. To get started with this extension, see the Quick Start third-party hardware drivers video on YouTube. And for more details on the OLED driver, see the Quick Look Micro OLED display video. There are also a couple of Zigbee green power device examples that make use of energy harvesting for their power, but I'll cover those in a future video. So let's create the Bluetooth Rail SoC energy harvesting sensor by clicking the Create button. The new Project Wizard window allows us to rename and alter the project settings. I don't need to do that here, so I'll just click the Finish button. We are then automatically moved to the Simplicity IDE perspective, and the project can be seen in the Project Explorer. If I open app.c, we can see how the PMIC APIs are used to initialize the PMIC and override its default configuration. The driver software component is already pre-installed in the example project. To compile the project, we can select the top-level project in the Project Explorer panel and use the Build button with a hammer icon on the toolbar. Compilation output is shown in the console panel. Once compiled, open up the binaries folder, locate the .s37 file, right-click and select Flash to Device. Then, in the Flash Programmer, click the Program button to transfer the binary. Once transferred, the Close button can be clicked. We now have the energy harvesting device running and can see the voltage level in the packets received by the observer device I have running. To see changing data, I can move the sensor away from the observer and watch the RSSI level displayed in the debug and on the OLED drop. I have a 10 farad capacitor storing energy, and this is more than enough to run the application overnight with the PV cell disconnected. The board upon waking makes 3 transmissions going into 1 second of EM2 sleep between them. Then it sleeps for a further 25 seconds in the EM4 sleep mode before repeating the cycle. Transmission times, capacitance, and the energy harvesting devices can all be adjusted to suit the application as required. So this can allow taking of readings from other sensors and adding appropriate data to the payload. Creating the projects for the observer and kinetic switch applications works in exactly the same way. Or you can make use of the Run button in the demo boxes to flash a pre-built binary to a connected board. If you want to explore further, you can get an energy harvesting kit via the Silicon Labs website. The GitHub README contains instructions on how to download and install the extension into the Simplicity Studio IDE. For details on using the hardware, see User Guide 591. This includes guidance on connecting hardware and taking current measurements from test points on the board. There is also documentation for the kit on docs.scilabs.com. To help you move towards more complete products, we have a white paper on Ambient IoT energy harvesting reference designs on our website. The first reference design is a solar-powered asset tag, using the same technologies we've seen on the dual harvester board, plus a PV cell from Dracula Technologies. It supports 24 hours of operation without a light source, and typically recharges within 15 to 20 minutes. The second is a similar tag, but this time an Energis power bridge harvests energy from RF signals. The hardware designs and software are available from GitHub for both these reference designs. If you want a step-by-step guide on creating Bluetooth applications making use of energy harvesting, check out the Practical Guide to Energy Harvesting for Ambient IoT course created by NovelBits. This course walks through the creation of a sensor, making use of the SparkFun BME 280 atmospheric sensor breakout, and is powered by PV cells. The course is free to view once you've provided registration information. Links to all the resources I've just mentioned can be found in the video description. This energy harvesting kit, featuring ePeasy's PMICs and Silicon Labs low-power wireless chips, makes it easy to start exploring the use of energy harvesting to power your Internet of Things applications. This is especially true of the dual harvester board that allows the use of vibration, RF induction and other technologies in addition to the photovoltaic cell we've seen today. If you're interested in powering Zigbee green power applications through energy harvesting, subscribe to our YouTube channel and look out for a future video. Don't forget, there are links to all the resources shown in this video in the video description. Thanks for watching.